Have you ever heard that matter exists only as solids, liquids, and gases? Maybe, at most, you've also come across plasma and supercritical states, but scientists have confirmed that these are just the beginning of a far more complex reality. In the shadowy corners of world-class laboratories and in the cores of the densest stars, there exist forms of matter that can flow through solids, light that binds together like a Jedi's blade, and crystals that oscillate rhythmically through time without ever stopping. Today, we're going beyond the limits of traditional physics textbooks to explore exotic matter, a frontier that could reshape quantum science and the future of humanity forever. Our journey begins at the coldest temperatures imaginable in the universe. Back in 1924, Albert Einstein and Satyendra Nath Bose predicted a state of matter that sounded like science fiction, the Bose-Einstein Condensate, BEC. Imagine thousands of atoms cooled to near absolute zero until they lose their individual identities and merge into a single superatom with a shared wave function. Physicists compare creating a BEC to trying to stop fast-moving atoms in a hailstorm. They use lasers from 6 directions to slow them down to a standstill. The result is a form of matter that behaves unlike anything else in the universe. In this nano-Kelvin world, we encounter phenomena that defy common sense, like superfluids. Found in helium-4 at extremely low temperatures, a superfluid has zero viscosity. It can flow through impossibly tiny pores, even climb up the walls of its container and escape without friction. At the electronic level, we find superconductors, where electrical resistance suddenly drops to zero. These materials also expel magnetic fields, a phenomenon known as the Meissner effect, enabling technologies like levitating trains and ultra-precise MRI machines. But the strangeness doesn't stop with bosons. In the quantum world, there are also fermions, particles like electrons, protons, and neutrons, which obey the Pauli Exclusion Principle, preventing identical particles from occupying the same state. To make them condense, scientists must trick them into pairing up into what are called Cooper pairs. These pairs behave like bosons, forming a fermionic condensate, a key to understanding high-temperature superconductivity. Beyond temperature, quantum structure and symmetry give rise to astonishing states like time crystals. While ordinary crystals repeat their structure in space, time crystals repeat their motion in time, like a heartbeat that never stops without consuming energy. This breaks time translation symmetry and could become the most stable memory for future quantum computers. Similarly, quantum spin liquids exhibit deeply entangled electron spins that never settle into a conventional magnetic order, even at absolute zero. For engineers seeking next-generation materials, topological insulators are especially promising. They act as insulators internally, but conduct electricity perfectly along their surfaces, protected by quantum symmetries. This makes them ideal for atomtronics, circuits built from atomic waves instead of electrons. Even more bizarre is the supersolid, which combines the rigid structure of a crystal with the frictionless flow of a superfluid. Now let's look to the skies. Under extreme pressure, exotic matter also forms in dead stars. In white dwarfs, we find electron-degenerate matter, while neutron stars contain neutron-degenerate matter so dense that a teaspoon would weigh as much as a mountain. Compress it further, and neutrons may break down into strange matter, made of strange quarks, possibly the most stable form of matter in the universe. Rewind to the first microseconds after the Big Bang, and the universe wasn't made of solids or gases. It was a quark-gluon plasma, QGP, a trillion-degree state where quarks and gluons moved freely. Surprisingly, it behaves like a perfect liquid with nearly zero viscosity. Studying it helps us decode the universe's earliest moments. At the cutting edge of experiments, scientists are now creating photonic matter,
getting masseless photons to interact and bind into molecules of light, behaving almost like the lightsabers from Star Wars. Meanwhile, in industry, there are also newly discovered and theoretical states like color glass condensates, dense walls of gluons and fast-moving nuclei, and superglass, which combines the disorder of glass with superfluid-like flow. These phenomena reveal that we are not just inventing new things, we are decoding and mimicking technologies already embedded in the architecture of the universe. Ultimately, understanding exotic matter isn't just theoretical curiosity, it's a gateway to a new golden age of humanity. From stable, powerful quantum computers to lossless energy transmission and ultra-precise gravitational sensors for space exploration, the secrets hidden in these extreme states are becoming the foundation of tomorrow's technology, once thought impossible.